This is what we have derived in the last class. We have actually found out the relation for relativistic mass, and relativistic mass is equal to m naught divided by root over of 1 minus v square by c square. So this is the relation for momentum, and if you put the relativistic mass, you get the relation for relativistic momentum. Now today what we are going to do is we are going to find out the relation of energy mass equivalence. So as all of you remember, E is equal to mc square is the relation, right? And we know basically that kinetic energy is stored in a system and can be expressed in terms of work done. Kinetic energy unit is joule, work done unit is joule. If you go by the definition of work done, basically it is in the form of kinetic energy that is stored in the system, right? So you basically can relate these two, and this is something which we are going to use to derive the relation E is equal to mc square. Before I start, you just remember this, that when I say E is equal to mc square, here the mass is relativistic in nature because we have the speed c involved. Okay, so that means this relation comes from the relativistic idea. Okay, so what we are going to do is we are going to write down the relation for kinetic energy and work done, and maybe just write it down as dk is equal to dw is equal to f dx, right? So work done is equal to force into displacement, and this is the relation that we can use, right? So if I just use your Newton's second law, we can say that this work done, which is equal to force, is nothing but rate of change of momentum. So d dt of momentum, and momentum is equal to mass into velocity into the displacement dx, right? Now an interesting thing to note here is that here we are taking d dt of m into v. Here both the mass as well as the velocity will vary. In general, when we do it, we say that mass is constant, so mass can be taken out of the differential, and I can just write down dv by dt, and then I can say it is mass into acceleration, that is force. But we are saying that it is moving at the speed of light. That means this mass actually will vary with time. This mass will vary with time. Don't write it down in your answer. I'm just writing it down as a note, with time. That means I cannot consider this mass to be constant and take it out of the differential equation, right? So that means if I just take d dt of two content a into b, okay, by the rules of differentiation, this is will be d dt of b plus b into d dt of a, right? So that's why I'm going to expand this, and I'm going to write it down as m d dt of v plus v d dt of m mass dot dx, right? We're just going to modify it a bit. This is dv, so I can take this separately. Okay, so I can write it down as m into dv, and then dt is there, dx is on the numerator, so I can just simply write it down as dx divided by dt. Similarly, plus I can take this as v, and then I can write it down dm, because this is dm, into
dx by
dx
dt.
dt, right? Okay, so that means we will have it modified, and this would be nothing but m dx by dt is v, so I can simply write it down as m dv into v plus this is dx by dt is v, dv is v square, so this is v square into dm. So this is a normal
dm.
maths problem, right? Yeah, so this is a normal maths problem, and I will mark this as number 1. Okay, now what we are going to do is we are going to have the relation for relativistic mass. We are going to use that relation because we know since it's moving with a velocity v, the relativistic mass relation will be valid here, so we are going to use that relation. Okay, so this is important. So we were going to replace it. Okay, whatever we have derived in the last class, we are going to use it. So that means in a way we can say this derivation is the application of whatever we have learned in relativistic mass, and here we know m is equal to relativistic mass and m naught is the rest mass. So let's use that. So m root over 1 minus v square by c square. We are going to use it later, but let me just write it down once, is equal to m naught, right? What we can do is we can try to modify this a bit. Okay, I'll tell you why we are modifying. Okay, so we'll soon know it. Okay, so what we are going to do is squaring on both sides. So if we square on both sides, we are squaring this term. So this is m square into 1 minus v square by c square is equal to m naught square. Okay, so I can take the LCM here and cross multiply, and there I can open the bracket. So if I do that, this would be m square c square minus m square v square is equal to m naught square c square. Right? If taken the LCM, c square gets cross multiplied here, and if you take the LCM, it will be c square minus v square. Open the bracket and you get this term, right? So we can have this relation. Okay, and what we can do now is we can differentiate this equation. Okay, let's differentiate this equation and see what we get. Okay, so here also the logic is the same, that m and v are not independent of each other. So if we differentiate this, c is a constant. So definitely in any frame of reference, moving or not, c is a constant. So c I can take it out, and I have to differentiate m square. That means if I do it like this, d of m square, I can write it down as d dm of m square into dm. So that means this would be nothing but 2m dm. Right, ddm of m square is 2m. So this is the term that I'm getting. So I'm going to use it here. So I'll be writing it down as 2m, c square is outside, and then here, right, minus, now this again is a part, m and v both are there, so I'm going to again differentiate this separately. So there is a minus, I'm going to take that minus. So first let me just differentiate with respect to m. So with respect to m, it will be 2m dm v square, right? So v square is there. Then the second time I'm going to differentiate it with respect to v. Okay, so that means now m square will remain outside. So if I again differentiate it, this would be 2 times of v dv. And then I have got the m square, right? M square is there, and then I differentiate v square, it will be 2v dv, right? So this is the term we have. On this side, m naught is the rest mass. Now I told you in the last class that rest mass is something which is a constant, because it will remain with the body and it will be a value which we have when the body is at rest. So that means this rest mass is a constant. C is also a constant. So if I differentiate them, it will be 0. So I'll have 0 on this side. So I can cancel out 2m throughout. This 2m, this goes, this 2 goes. We have got m squares, only 1m remains, right? So if we do that, we can actually have our simplified equation as c square dm is equal to, so c square dm I'll take it on this side, and the minus I'll take it on the other side, it will become plus. So this would be nothing but equal to v square dm plus mv dv. Remember, one m is here and v mv dv. So this I will mark this as number 2. And what we see here is that 1 and 2 have got the same right hand side, right? So this is equal to this, correct? And what is this? Okay, if we just write down a bit more here. What was all this? This was dw, okay? So this was dw on this side, and dw is equal to nothing but the kinetic energy. Right, so we'll start with that relation. So that means dk, if we compare these two relations, dk is c square dm. Okay, so dk is equal to c square dm. So I'm going to just write down that now. Okay, so what we are going to do is comparing 1 and 2, dk, which is on the left hand side of equation 1, is equal to c square dm, which is on the right hand side of equation 2. So this is the relation we have. We need the total kinetic energy, so that means we are interested in integrating it. So we can integrate this. Okay, so let me just integrating. So dk integrate, it would be k, is equal to integration of c square dm. Now this is going to be a definite integral because when a body starts from rest, its mass is m naught, and it starts moving and achieves some velocity. That velocity maybe the mass is m, right? That means the lower limit would be m naught. It starts from m naught, and the upper limit would be m. Logical, right? Because integrating with respect to mass, and we know what is the limit of mass when a body is moving because we have already studied this in idea of relativistic mass. So let's just do the integration. So this is c square, this is m, dm integration ka m ho gaya. This is from m naught to m. That means this would be nothing but c square into m minus m naught. Upper
M
limit
naught.
minus lower limit. Yeah. So this is mc square minus m naught c square. So ये क्या है मेरा kinetic energy. This is my kinetic energy, right? Now imagine a body is at rest. From our preliminary knowledge of work energy which we have studied in our lower classes, we know that a body may be at rest or may be moving. The total energy is constant. The total energy is kinetic energy plus potential energy. When the body is at rest, it will still have some energy. That entire energy would be nothing but the potential energy because it is not moving. As soon as it moves, it will be basically having both kinetic and potential energy, and as soon as it goes completely away from its motion, I mean totally in motion, it will be having only kinetic energy. So the entire potential energy will be converted into kinetic energy. So this rest energy is nothing but m naught c square. This rest energy is nothing but m naught c square. And when we talk about total energy, okay, total energy, we have it as kinetic energy plus potential energy, and this rest energy is actually nothing but potential energy. So that means if I want to find out the total energy, let's represent it as E. Okay, let's represent this as E is equal to kinetic energy. We have just now found out the kinetic energy when the body is in motion. This is nothing but mc square minus m naught c square plus potential energy, which is m naught c square, right? So we have got our relation E is equal to mc square. So simple, right? So this and this gets cancelled, and we have got mc square. So in general, when you look into this expression, okay, and without any maybe any background, we feel that okay, this mass is any mass whatever we realize in our daily life, okay. But not, that's not true. This mass, if you look into this relation, is differentiated into m and m naught. M naught is the relativistic mass, and m naught is the rest mass. M is the relativistic mass, and m naught is the rest mass. Okay, we can of course write it down in terms of rest mass by using m naught by root over 1 minus v square by c square. Okay, but here we are saying that this is the relativistic mass. Okay, so whenever we are actually going to study, because now we know what is the difference between relativistic mass and normal mass. In general, whenever we write down m, and if the body is moving with some velocity, this value is always relativistic mass. It is always relativistic. Maybe this velocity is very small, still it will be relativistic. But the thing is, when we put it into this relation of m is equal to m naught divided by root over 1 minus v square by c square, this becomes very small, so we basically consider it to be m naught. So m naught and m are the same. Okay, so in our day-to-day life, m and m naught are the same, but if you think about it technically or scientifically, m is always the relativistic mass. If a body is moving, you are considering mass, you are always considering the relativistic mass. Okay, so that is the basic idea. So this was the application of relativistic mass we have used to derive E is
Sir,
equal to mc square. Yeah, tell me.
sir, sir, if you are saying that M and M not are same, then why are you not writing them same?
Yeah, so as I said, okay, as I said, it depends under what condition you are basically considering them. Okay, for example, if I'm considering it to be, let's say, on a day-to-day life, if I'm considering the speed to be 100 kilometer per hour, This is my velocity, right? This is something which I've already explained it before. V is equal to 100 kilometer per hour. That means root over of 1 minus v square by c square. If you calculate them, this will be very close to 1 because this is a very small value and this c is very large, right? C is 3 into 10 to the power 8 and then you are squaring it. So 1 divided, a small value divided by a very large value would be very equals to 0. So this is root over of 1 minus, so this is 1. So if I write down m is equal to m naught in this kind of cases, this is okay, not a problem. Okay, because this is, this is the limiting condition. Okay, so m and m naught may be equal if the speed is low, but if the speed is high, if the speed is very high, that means comparable to the speed of c, m and m naught won't be the same. That's the basic difference between a moving mass and a mass which is not moving, relativistic mass. Okay, so for a better idea on this, we have already discussed this in the last lecture, because based on this idea only we have derived this relation of m is equal to m naught by root over of 1 minus v square by c square. Okay, now if someone asks you, okay, you are doing a normal problem, okay, maybe in since you are from computer science, you are doing some simulations, so you're considering a mass, you can consider the mass whatever is provided. Okay, but technically, okay, somewhere in the back of your mind that this mass is actually the relativistic mass. We just don't consider the concept of relativistic mass because the velocity is very low. So mathematically this result is very close to 1. So that's why relativistic mass and the rest mass are the same in our day-to-day life. Okay, but then this example I've given again and again. If you consider the Large Hadron Collider experiment in Switzerland-France border, where they are trying to mimic the Big Bang, they are trying to take two particles, maybe two protons, and allowing them to hit each other at a very fast speed. The speed that they are considering is very, very high. Okay, they are using a cyclotron, particle accelerators and all, and they are hitting those particles. They are moving at a very fast speed. There, if this mass, rest mass of the proton and the mass when it is moving are considered to be equal, whatever calculations they are going to do will be wrong. It will be entirely wrong because they did not consider the relativistic effect. So in general, the relativistic effect is there only at high speed. Relativistic effect. Relativistic effect at high speed. That means comparable to the speed of light. Comparable in the sense, if you take it to be 3 into 10 to the power 7 to 3 into 10 to the power 8. If you go to 10 to the power 6 also, then also you'll see that these values will become almost insignificant. Okay, so relativistic effect. Based on this relativistic effect, a new field of physics has also come up. Okay, and this is a different branch altogether. We don't have much of study syllabus in here in India, but people are actually studying this. This is relativistic quantum mechanics. Quantum mechanics. So our next unit is actually based on quantum mechanics.